All right, so this video is going to be about titrations. Titrations are essentially ways of doing calculations for reactions where both things are aqueous. They are typically acid-base reactions. So I'm mostly going to focus on acid-base neutralizations, which we have seen how to balance those equations, but we need to know how to deal with the number side of things. So the last video we learned how to deal with if you have limiting reactants, and there was a three-step process, and it was always the same three steps in the same order every time. Titrations, the method kind of varies. Okay, so I'm honestly just going to kind of work through an example and kind of show you how to approach this. I'm going to do a lot of examples, even if I have to do a couple videos. So we'll see what I can do here. So first things first, I want to remind you that molarity is moles per liter. Okay, so in the previous video, we converted from grams to moles a lot using the periodic table. Anytime you need to convert from volume to moles, molarity is what you need. So it's similar to the last problems, but it's molarity based. Okay, so we want to know how many milliliters of 0.500 molar HCl would be needed to neutralize, let's say 17.50 milliliters of 0.625 molar KOH. This is a typical titration problem. We have an acid and a base reacting, and we need to know, usually we'll know the volume and the concentration of one of the two, and we're solving for either the volume or the concentration of the other one. These are not the only way to do it, but these are the most common types of titrations. Okay? So the very first step, no matter what, is to write out the balanced equation. Okay? Because part of this process involves the mole ratio, and if you don't write the balanced equation, you can't do the mole ratio. We learned how to do this a few videos ago, but write down your charges, plus 1, minus 1. This one, I intentionally picked an easy one. Plus 1, minus 1, we switch the negatives. So H and OH makes water, which is fine, it's an acid-base reaction, and K and Cl come together. Water is inherently neutral. This is plus 1, minus 1. Okay, we don't actually care if they're aqueous or solid in this one. We just need to know how to balance it. So in terms of balancing, we have one chlorine, one potassium, 2 hydrogens, one oxygen. I intentionally picked one where it's really, really easy. We will see later examples where there are coefficients and it makes things more complicated. Okay. So now that we have our balanced equation, what we're going to do is we are going to start with the compound that we know both the volume and the concentration for, and we are going to solve for moles. So since we're visualizing molarity as our conversion factor between moles and volume, I'm going to get this to liters and then use this to convert it to moles. Okay? So I have 17.50 milliliters, and I'm going to convert that to liters by dividing by 1,000. Because molarity is moles per liter, I need the units to cancel. Then we're going to take it times the concentration of the same solution. It's important that you keep track of which one is which. And molarity, even if it's written as capital M, means moles per liter. So we can cancel that out. Now we have solved for moles. Okay, so the first step, we have moles of KOH. And the reason we chose to start with this is because we knew both the volume and the concentration, we could solve for moles. Now we do the mole ratio. This one is a 1-to-1, which is not going to affect any of the numbers, but I'm going to write it in here just so that you can, if you look back at the problem, you'll know why these numbers are here. Okay, so the next step is the mole ratio. Okay, now depending on what you're solving for, this next part's going to be, it varies a little bit. We are solving for volume. If we canceled everything out, we would have moles of HCl, and since we know the molarity, we can solve for volume. So I have moles of HCl on top, so I need the 0.500 moles, we're going to run out of space, HCl per liter on top, and I'm just going to continue down here. The question asks for milliliters. We have liters, so 1 liter, this was on top, so this has got to go on bottom. 1,000 milliliters is going to go on top. So you'll note this is a little more cumbersome than the last video's type of problems, the limiting reactant problems. So in terms of typing it in, we have 17.50, and honestly we're going to divide by 1,000 and then later we're going to multiply by 1,000, so I'm just going to ignore those. You may occasionally have to type those in, but for this one they cancel out. Then times 0.625, we don't have any mole ratio numbers in here, then divided by 0.5. Oh, well, I hit multiply. Sorry, let me try that again. 17.50 times 0.625, it equals divided by 0.5. And I get an answer of, I guess, this has 4 sig figs, but these have 3. 3 sig figs would be 21.9 milliliters. So the idea is, if you had, these are the two concentrations, and you had 17.5 milliliters of the base, this many milliliters of acid would cancel it out. And it makes sense that this number is going to be a little bit bigger because the concentration's a little bit lower. You have to make up the difference. Okay, let's try another variation. All right. Okay, if it takes 13.58 milliliters of 0.119 molar H2SO4 to neutralize let's say 20.00 milliliters of we need a base. Let's go with NaOH. We want to know what is the molarity of the NaOH. So in the last problem, we had the molarity of both and we knew the volume of one and we're solving for the other volume. This time we have both volumes, we know one of the molarities, we need to solve for the other one. Okay? Either way, no matter what you're solving for, the very first thing you do is write the balanced equation. So we have H2SO4 reacting with NaOH. Okay? Charges, H is +1, sulfates -2, sodium +1, hydroxides -1. Switch the negatives like we usually do, as we have seen before. Then we're going to end up with H and OH makes water, and Na and SO4 is the other compound. The charges here, Na is +1, sulfate is -2, so we're going to need 2 of these to cancel it out. Water is inherently neutral. Okay? So, what we usually did in the past was we would figure out the state symbols. It doesn't actually matter for this. What we care about is balancing it. We've got neutral salts, now we need to balance. Okay, sulfates, we have 1 here, 1 here. Sodiums, we have 2 here and 1 here. So I'm going to put a 2 in the front. That gives us 2 H pluses and 2 OH minuses, which should make 2 waters. But the important part for this problem is that for every 1 mole of H2SO4, it's going to take 2 moles of NaOH to cancel it out. So the way we start this problem is we take the compound that we know both the volume and the concentration for, and we solve for moles. This time it's H2SO4. So we have 13.58 milliliters. Molarity is moles per liter, so I'm going to convert this to liters. The concentration is 0.119 moles of H2SO4 per liter. Milliliters cancel out. Liters cancel out. All of this together would give us moles of H2SO4. And we are solving for that because it's the one we know the concentration and the volume for. Okay, the next step is the mole ratio. Based off this balanced equation, for every 1 mole of H2SO4, which is going to be on the bottom because we need it to cancel out with this one which is on top, we should need 2 moles of NaOH to cancel it out. Okay. Now, here's where the problem's a little bit different than the last one. So I guess I could label this mole ratio. Okay. If we canceled everything out right now, we would have moles of NaOH. To get molarity, we need moles per liter. Well, we're going to stop here because this will give us moles, and then we can divide it by the volume in liters. So, 13.58 divided by 1,000 times 0.119 times 2. I got a very small number, which is fine. 0.00323, I guess 3 sig figs, 0.00323 moles. I'm actually going to write all the other numbers, but that's where our sig figs end. And that's how many moles of NaOH were in this process. Now, to get the molarity, we know the moles, and this is the volume. We're just going to convert this to liters and then take moles divided by liters to get molarity. So we get 0.02000 liters. So molarity is moles per liter. We have moles here and liters here. And you just divide them, and whatever the answer comes out to, that's what we get. So whatever the answer was, divided by 0.02, 0.0000, not that it's going to impact anything, but whatever. And I got a concentration of 0.162, I guess, when we round it to 3 sig figs. Okay. So you'll note this is not the same setup as the last one, but it's not completely dissimilar. The beginning part's going to always look the same. From after the mole ratio, it's going to kind of depend on what you're solving for. If you're solving for volume, the first problem's the right setup. If you're solving for molarity, this is the right setup. But both of them are really, really common, and it kind of just depends on the situation. Let's try one more other variation that is different from those two, and we'll see how it goes. Okay, it is possible to do titrations with one of the compounds being a liquid and the other one being a solid. So let's try that. So we want to know how many milliliters of point, I don't know, 250 molar, let's go with HBr. How many milliliters of this would be needed to neutralize 12.3 grams of KOH? So now this one's a little different because this is a mass. Okay, so we don't know the volume and the concentration with this HBr, but because we know the mass, we can use the periodic table to convert to moles. So that's what we're going to do first. I'm thinking 12.3 may have been a really big number, but that's okay. If we get a huge answer, we'll just deal with it. So what we do is we add up potassium, which is 39.098, and oxygen, which is 15.999, and hydrogen, which is 1.008. And I got 56.105. And that's grams per mole for KOH. Okay, so this will actually feel like one of the limiting reactant problems. This was kind of the first step we did on that. So, same idea though, we solve for moles. Oh, actually, I guess I forgot to write the balanced equation. Let's do that real fast. sorry, HBr plus KOH. This one's actually going to be pretty easy again. Plus 1, minus 1, plus 1, minus 1. We end up with KBr and H2O. That's plus, that's minus, that's neutral, that's neutral. We have one bromine, one potassium, two hydrogens, one oxygen. So it's a 1-to-1 ratio again. That's probably why I forgot to write it down, as I remembered it being a straightforward one. So we do the mole ratio. For every 1 mole of KOH, we will need 1 mole of HBr to cancel it out. Oops. HBr. Okay. So, not dissimilar from what we've done before. So this is the mole ratio. And now we know the concentration of HBr, so we can solve for molarity. Or sorry, we can solve for volume. This is actually really similar to the first titration problem we did. So we're going to divide by the concentration, because this will be moles of HBr on the bottom per liter. And we're looking for volume, but if we have volume at this point, we're asking for milliliters, so 1 liter would go on the bottom, 1,000 milliliters will go on the top, which is why I'm anticipating this being a big number, but that's okay. So we're going to take 12.3 divided by 56.105, hit equals, multiplying and dividing by 1 doesn't do anything, divide by 0.250 times 1,000. Wow, we're going to get a huge number. Okay, apparently it would take 877 milliliters. I probably should have picked a much smaller mass. That's okay, this is what the answer is. So, if we weighed out 12.3 grams of KOH, which is a base, it would take 877 milliliters of 0.25 molar HBr. Obviously, if we jacked up the molarity, we would need a much smaller volume. But this is what we had to work with. This is how the problem works out. All right, I will try my best to also post other examples on OnCourse for you guys to practice with, but this is it for the video. All right, thank you.